Well, hello everybody, and I hope you're fired up to talk about multiplying some polynomials tonight. I think it's going to be a really fun topic. I think you're going to not only be really good at it, but enjoy it along the way. But before we dive in and talk about multiplying polynomials, I wanted to surprise you a little bit tonight here in the first slide and talk about different careers in math. And this is one of my ideas this year is to kind of start a bunch of the videos off randomly throughout the year talking about different careers in math, because a lot of times over the last couple of years students have come to me at the end of the year and said, well, I seem to be kind of good at math, I seem to have a talent, but I don't know what the heck to do with it. Does that mean my options are to be a math teacher or what? But I want to let you know that there's a lot of options beyond becoming a math teacher. And certainly one of the common denominators of all these careers in math is that outside of teaching, they seem to involve very high salaries. And I certainly don't want you to think that that should be the number one decision influencing your decision. But seems to be a lot of money in careers in math, whether it's engineering or and so forth. So tonight's the career is biomathematics, and it says here, starting with the second sentence, it models natural and biological processes using mathematical techniques and tools. Results have been applied to areas such as, get this, cellular neurobiology, epidemic modeling, or population genetics, just to name a few. So if if you seem to have a talent in biology and math at the same time, and you want to kind of link the two together, or if you just enjoy being outdoors, you enjoy working with plants, animals, etc., then certainly Google this topic, and you might be surprised to learn more about it. Okay, so now we're going to dive into our theme tonight. We're going to talk about multiplying polynomials, and basically all we've got here is it's the repeated use of the distributive property. And I would tell you, of all the properties that we've flirted with over the last couple of videos, we've talked about the commutative property and the associative and the distributive property. I would say the one we use the most by far is the distributive property, and coincidentally I think it's the one we're by far the most comfortable with. And so tonight we're really going to expand our understanding of the distributive property. As much as you've used it over the last couple of years, we've kind of used it in a limited fashion, and we're going to totally expand how you look at and think of the distributive property. So in the past, we've done this a lot. We've multiplied a binomial times a second binomial, and we've always used something called Foyle, and it stands for first, outer, inner, and last. Well, believe it or not, Foyle is just repeating the distributive property twice, okay? And so let's talk about that before we can expand it beyond binomials. So when we talk about the product, here's what we're going to do first. We're going to take this term 2x, and I'm going to distribute it to 3x squared and distribute it to negative 4. And so 2x times 3x squared gives me 6x to the third. Notice how I added my exponents. And then 2x times negative 4 gives me minus 8x. Next, okay, so that was the first use of the distributive property. Now we're going to repeat it, and we're going to take positive 5 and we're going to distribute him twice, once to 3x squared and once to negative 4. And that would give me 15x squared minus 20. And I would say of the four terms, none of them are like terms, so I can't go any further. The only thing you might consider doing is rewriting them in standard form so that they go in the proper order. Notice how we started with the term with the biggest exponent, 3, and worked our way down to the term that didn't have an exponent. So things are about to get a little crazier, okay? So buckle that seatbelt here. We're going to we've got a binomial multiplied by a trinomial, and this is probably the first time we've ever tried this. But again, it's just repeated use of the distributive property, and so we're going to take our time. I'm going to take 3x, and I'm going to distribute it to 2x squared minus 6x and negative 5. And as I do that, I'm going to get 6x cubed minus 18x squared minus 15x. Okay, so at this point we're about halfway done. Next thing we're going to do is we're going to take negative 2 and we're going to start all over, aka repeat the distributive property. I'm really having a tough time spitting that word out tonight. So we're going to distribute it to all three of the terms, and that would give me minus 4x squared plus 12x plus 10. Notice a couple of times there I had a negative times a negative. So now I'm going to take a step back and I'm going to combine my like terms. I can combine my x squareds together, and I can also combine these x's together, thus giving me a final answer of 6x cubed minus 22x squared. Notice when I combined these two terms right here, I added the coefficients to make negative 22, but the exponent stayed squared. And then I'm going to get minus 3x plus 10, and that, ladies and gentlemen, is my final answer. Now, before we go on to the next question, I want to dig into a little deeper into this one. And it says here, and this is really a really good thing to put in our notebook, it's important to understand that our final answer is equivalent. And again, this is one of the most powerful words in all of mathematics, equivalent, to the original expression, and this equivalence can be tested. Okay, so while we're on a test, you may be wondering, my goodness, I've got a little extra time here. It would sure be nice to know, how confident I am in this answer. And all we're going to do is, you could pick any random number you want. Maybe we could say 10 is your favorite number. So we're going to plug a 10 into the original expression, see what we get for an answer, and then we'll plug 10 into our final answer and see if we get the same answer. And of course, knowing that they have to be the same, that would be our way of checking them. Okay, our next big task here is to try to multiply three binomials together. And again, it seems very overwhelming, and I don't think this is anything we've ever flirted with before. But just to get us warmed up, I want you to think about, what if you just wanted to multiply three numbers together? What if we said, let's multiply 2 times 6 times 5, right? What you would do is, you'd go left to right, and you'd say, well, 2 times 6 is 12. And then after you got done multiplying the first two numbers, now you'd multiply the 12 and the 5 to make 60. So really what we're going to do here is we're going to focus on, and you could put some imaginary brackets here. And what that's going to do is that's going to remind me to just FOIL the first two binomials together first. And again, we're just thinking distributive property, multiple repeated times, x squared minus 3x. Then I'm going to distribute the 4, and that's going to give me plus 4x minus 12. And what I'm going to do is I'm going to clean that up to make x squared plus x minus 12. And we'll put parentheses around that bear. And then just take this x plus 8, who has just been chilling for a little while, and bring him straight down. Okay? And now, again, we're still distributing. So let's take x squared and distribute him to the x and to the 8. And that's going to give us x cubed plus 8x squared. And then we'll start with this positive x and distribute him twice. And that's going to give me positive x squared plus 8x. And then last but not least, we'll grab this negative 12 and distribute him twice to give us negative 12x minus 96, I believe. So again, now we'll just combine like terms. I only have 1x cubed, but then I'm going to have a total of 9x squareds and a total of negative 4x minus 96, and we'll put a box around that. There's our final answer. Now let's take this discussion a little bit further here. Now this particular polynomial right here that we finished with has 3 zeros, okay? And we've briefly talked about this. What is a zero? It's an input value that causes the final answer to be 0, okay? And what I mean by input value, it's a number that you plug in for x, okay? So here's my question. Is x equals 2 a 0 for this particular polynomial? And how I'm going to find that out is I'm going to substitute a 2 in for each of the x's. Notice I'm using a lot of parentheses, and the parentheses really pay off if our input value is a negative number. And as we start to clean this up, I get an 8 here, I get a 36 for the second term, minus 8 minus 96, which gives me a grand total of negative 60. Therefore, my answer is no, x equals 2 is not a 0 for this particular function. Now, my next question is, can you anticipate what 3 values of x are actually the zeros? And there's a really easy, sneaky way to do this, and I'm going to let you in on a big secret here. And what's going to happen is, I'm not going to necessarily look at my final answer, because that's really hard to anticipate. But if you go back up to the original expression right here, all right, and you look at this expression right here, you'll always be able to tell what the zeros are just by looking at this expression. For instance, one of the zeros is going to be x equals negative 4. And you're wondering, how in the world did I know x equals negative 4 is going to be a 0? Well, think about plugging it in right here. You'd say, well, negative 4 plus 4 is 0. 0 times this expression times this expression equals 0. Again, 0 times anything is 0. My second 0 would be x equals 3. And I knew that because if I look right here, if I substitute a 3 for x, 3 minus 3 is 0, and again 0 times this expression and this expression is again 0. The third 0 is going to be x equals negative 8, and what I'm doing is I'm looking right here and I'm saying, well, negative 8 plus 8 is 0, and again 0 times any other expression, 0. So basically what I'm doing is I'm saying the opposite of positive 4, the opposite of negative 3, and the opposite of positive 8 are going to be my three zeros. So far tonight we've talked a ton about the distributive property, and now I want to share with you an alternative method called the tabular method. And some of you are going to like this a lot better than the distributive property we just talked about, okay? And everything here hinges on the fact that you need to understand that the area of a rectangle is found by multiplying the length times the width, which I think we're really good at. So let's take a look at my first rectangle I have here. Maybe I would say the length is, let's say, 7x, and maybe the height or the width we could say is 2x, and the area then becomes 14x squared. Okay, so we're just kind of warming up here with our area. Let's think of another rectangle here. Maybe the length is going to be, let's say, a 10, and maybe the height is 4x squared, and the area of this rectangle would then be 40x squared, and I'm just multiplying the 10 and the 4x squared. One more warm up here. Let's say our length is going to be, let's see, 6x, and our height or our width is going to be 5x squared. The area would then be what? 30x cubed. Again, multiply the 6 and the 5 to make 30, and then add the respective exponents to get a 3 because there was an invisible 1 right there. Okay, so here's our first live example, and they want us to find the product of two binomials, which again, we've already talked about. We could FOIL them, but we're going to try to learn the new method here and see which one you like better. So the tabular method says, since it's a binomial times a binomial, I'm going to draw a 2 by 2 box. Okay, and let's see, we can kind of split these roughly down the middle, doesn't matter. Now the first binomial was 2x plus 4, so I'm going to put a 2x and then a 4 here. The second binomial was 5x plus 2, so I'm going to put a 5x here and a positive 2 here. And what I'm going to try to do here, my keys, number one, I'm going to find the product of each individual rectangle first. Okay, so here's what I'm thinking. The first rectangle has a length of 2x and a width of 5x, so the area would be 10x squared. The second rectangle has a length of 4 and a width of 5x, so his area would be 20x. Let's see. The third rectangle, the dimensions are 2x and 2, so the area is 4x. And then the last one has dimensions of 4 and 2, so the area is 8. Now what I'm going to do is I'm going to find the sum of all the rectangles, and remember, we're only allowed to combine like terms. So here's what I'm getting. If I add all of those rectangles together, I'm going to get 10x squared, and then I can combine the 20x and the 4x to make 24x, and then the last term would be an 8. And that's the same answer we would get if we use the distributive property, aka foiling. So that might have looked like the strangest thing you've ever done, but I bet once we get a couple of examples under our belt, some of us are really going to fall in love with this method. And we're going to try to be good at both of these methods, and then when we get to the test, we can kind of pick whichever one we're more comfortable with. So here's what I did. Again, I drew a 2 by 2 box just because they were both binomials, and I'm going to go 4x squared here and a positive 3 here, and then I'm going to go 2x cubed on the side and a negative 6 here. And again, I'm just going to try to find the product, or aka the area of each rectangle. And my first rectangle, if I multiplied 4x squared times 2x cubed, I've got 8x to the 5th. My next rectangle is going to give me 6x cubed. And my third rectangle is going to be negative 24x squared. And my fourth rectangle here is going to give me negative 18. And now I'm just going to try to find the sum of all four of those. And whether you look at this as good news or bad news, I don't think we've got any like terms. So my final answer is 8x to the fifth plus 6x cubed minus 24x squared minus 18. And again, this is the same answer we would get if we use the distributive property. Now the only curveball here is that my second polynomial is now a trinomial right here. So what's going to happen is my rectangle, I'm going to go 2 across, but then I'm going to go 3 blocks down this time. Alright. And you could do the opposite. You could do 3 columns and 2 rows, but I'm going to go 2 columns and 3 rows here. And what I'm going to do is I'm going to 3x and plus 7 across the top, and then down the side I'm going to use 2x squared, negative 4x, and then positive 9. And again, I'm just going to try to find the area of each individual rectangle. And feel free to hit the pause button here and try this one on your own, and I'm going to go ahead and fill in each of my areas, hopefully without making any goofy mistakes here. I'm going to try to stay on top of my game. Minus 28x. And then this one would be 27x and 63, I believe. So now that I've found the area of each individual rectangle, I'm just going to find the sum of all 6 rectangles. And that's going to give me 6x cubed. And then I think I can combine these two together to make positive 2x squared. And then I can combine these two together to make negative x plus 63. And again, we'd get the same answer if we had used what? Yeah, the distributive property. Alright, so I hope you had a great night. Hope you enjoyed multiplying polynomials, and I will see you tomorrow.